Okay, so let's get started. We welcome you to the second lecture on topics of reinforcement learning. Last time we talked about deterministic finite horizon dynamic programming problems. Today we're going to focus on stochastic finite and infinite horizon dynamic programming problems. And here's the outline. We're going to do a review first of the deterministic case, and we're going to talk a little bit about approximation in value space. How do we do approximate dynamic programming for deterministic problems? This is going to be very brief, an introduction to the more extensive discussion of approximation in value space for stochastic problems. Then we're going to talk about a stochastic dynamic programming algorithm, and we are going to illustrate it with an important type of problem, linear quadratic problems, a linear system and quadratic cost function for one dimension. It's going to be an easier calculation for one dimension. And this is a very basic and important problem in control system design. And it's also a very favorable case because it admits an analytical solution by dynamic programming. So we're going to have the opportunity to see how dynamic programming works in the few problems where an analytical solution can be found. Then we're going to talk about approximation in value space. This is going to be our reinforcement learning workhorse. It's a fundamental approach that we're going to spend practically the entire semester on. Approximation in value space, where we approximate value functions or cost functions. And we're going to summarize this, review it, and then we're going to contrast it with an alternative approach, which is approximation in policy space, where we try to approximate policies. And we're going to see how these two can connect. All of this is going to be for finite horizon problems. And then we're going to discuss briefly infinite horizon problems, an overview of the theory and of algorithms. And we are going to illustrate the theory and the algorithms with linear quadratic problems after we extend them to infinite horizon. We're going to take a break right around here, and hopefully we will not need another break. So, review of finite horizon deterministic. Here we have a system that generates a sequence of states, x0, x1, and so on, up to a finite horizon n, up to xn. The next state is generated from a current state according to a system equation where the control enters. And the control is chosen from some set that depends on the current state. Now, one thing that I mentioned last time, and I want to emphasize again, is that this formulation is very general, except for deterministic. This is very general. The control and the state spaces are arbitrary. They can be vectors in some Euclidean space, Rn. They can be chess positions taken out of a finite set of all possible chess positions. They can be word strings. They can be anything. So that enhances the generality of everything we're going to discuss. We want to bring out the fundamentals at the highest possible level of abstraction so that we can apply them as generally as possible. Okay, so each transition also has a cost, G, that depends on state and control. The cost function that we use is the cumulative sum of the cost of all the transitions, plus a terminal cost that depends on the final state. Now, given an initial state and given also a sequence of controls, the cost is a number, it's given by this expression. So it depends on x0 and all the controls. And what we want to do is find the optimal cost function, minimize overall sequences of controls that are feasible. And after we do that, what's left is a scalar that depends on x0. It's effectively a function of x0, and we call it the optimal cost function. It's a very fundamental object in this problem formulation. So we discussed the dynamic programming algorithm and the principle of optimality, which computes the optimal cost of all the tail subproblems that start at a given state xk at a stage k. We call this the J star values, okay? There are many of those. Dynamic programming will compute all of those, and it will start at the terminal stage with just the terminal cost function. We'll go one step back according to this equation by minimizing the sum of the next stage plus the optimal cost of the next tail subproblem, which we have computed it because we're going backwards. So from Jn star, we go to Jn minus 1 star, Jn minus 2 star, and so on, all the way to J star 0. At that point, we have the tail subproblem, which is just the original problem. So we have gotten J star, the optimal cost function of the problem. Now, it's possible to obtain an optimal solution by generating by keeping track of all the controls that we obtain by minimization of this equation. However, we can also, after we finish with all the J stars, go forward in an online play fashion, start with the initial state. We know J1 star, we minimize here, we obtain the first optimal control. We plug it in the system equation, we get the first optimal state. Then we obtain U1 star, then X2 star, by this minimization, then X2 star, then U2 star, and so on, all the way to the end, generate the entire trajectory. So that's the dynamic programming algorithm, very simple justification, lots of intuition, but also lots of computation for this calculation, which you can view as offline training. If the state space is very large, this computation is exorbitant. Think of a traveling salesman problem with a very large number of cities, right? The state space, the size of the state space grows exponentially. So that's the reason we have reinforcement learning, to simplify things here. But before we go into that, let's look at the concept of a Q factor. The Q factor is a function of state and control pairs. And for xk and uk at stage k, it takes this form. It is the cost of the immediate cost using uk plus the optimal cost to go from the next state. So it can be viewed as the cost that you would obtain if you were to use uk at xk and then act optimally afterwards. So if you know the J stars, then you can compute the Q stars. But also, if you know the Q stars, you can also compute the J stars. You can recover them by minimization here. What is this minimization? It's minimization over U of this expression. But that's exactly the dynamic programming algorithm. So this is J star K of xk. So if you know one, you know the other. This one requires more storage than this, but it has some advantages, conceptual advantages and algorithmic advantages that later on we're going to discuss. Now, one thing to note is that the dynamic programming algorithm can be written equivalently in terms of Q factors. The Q factor is defined by this expression, but this expression is obtained by minimization of the Q factor at time k plus 1. So combining these two equations, we have this. So we can generate all the optimal Q factors sequentially going backwards from time n to time 0, according to this algorithm. Now, algorithms that are based on Q factors arise in several different settings in reinforcement learning. Collectively, we'll call them Q learning. There's no one Q learning algorithm. There are several of those, and they all share the feature that they calculate exact or approximate Q factors by using some kind of iteration. Okay, so now let's get into approximation in value space. We mentioned that computing the J stars is very difficult, very time consuming. So we replace those with an approximation J tilde for each stage. This is a function of the state xk, and it is the exact optimal cost. We replace it by an approximation. How we get this approximation, let's not worry about for the moment. However, we can use this J tilde during online play to generate a sequence of suboptimal controls. At time 0, we minimize in this expression to get U tilde 0, a control for the first stage. Then we get the state at the next stage, x1 tilde, according to this equation. And once we know this state, we can do this minimization and get U1 tilde and go forward, U0, then U1, U2, and so on, all the way to the end. Now, this is a much easier calculation than the calculation involving J star, the J stars. And that's why we do it, and that's why it is the principal method in approximate dynamic programming. Of course, the question arises, how do you get this J tildes? This is one of the principal issues in reinforcement learning. We're going to be talking about it extensively in this course. Let me give you some ideas. One possibility is offline problem approximation. Okay, we have a difficult problem. Suppose that there's a simpler problem that looks like it, okay? And it's so simple that we can solve it offline by exact dynamic programming. Then we can use the solution of the simpler problem as an approximation to the optimal cost function of the original problem, okay? Maybe it's a problem with smaller dimension. Maybe it's a problem with less difficult non-linearities, whatever. Another major approach, obtain J tilde from some parametric class of functions. In other words, functions of the state, we parameterize it with a parameter R, and we use training from data to obtain good values of R. This is the typical approach that you use in the context of neural networks. We use a neural network which has weights, and therefore this parameter R, and we find parameters that sort of match as best as we can tell the optimal cost function. And a third approach, which I'm going to illustrate shortly, is rollout with a heuristic, and I'll explain this in the next slide. Any questions here?
Do you assume that the optimal cost has to be the global optimal? Because why do we assume we can obtain always we can obtain the optimal value of a function? If a function the system non-convex, then maybe sometimes we get one local optimum, then another time we get another local optimum. How does that impact the dynamic programming? And if there is a problem where you don't know how to obtain the global optimal solution.
Okay, dynamic programming does not deal at all with local optima. It's always global. Okay, it's a global optimum. That's the nature of the algorithm, and you can prove that from the calculations that we did. When you solve the traveling salesman problem in the example, you found a global optimum. There's not even a definition of local optimum in this context. It's only global optima that we're dealing with in this course. Local optimality has to do with gradient methods that can be attracted to some local, but not dynamic programming. That's one of the advantages, by the way. It cannot get stuck into a local optimum. Of course, when we go into reinforcement learning and we use gradient type methods or other methods that are deviations from dynamic programming, then we may have to deal with local optima. But generally speaking, that's not a concern for us. It's always global.
Function. How would dynamic programming just have the mint operator, but that mint operator does not have the if I just have like, I don't know, a function, sine x squared, or something like that, how would we, like, how do we implement them in operator? The limit of it doesn't tell us how to do it. As you said, the way we know how to do it is gradients.
Okay, so you're referring to the case where this minimization involves a continuous variable. Then we assume that we can find a global optimum. Of course, that's a big assumption, and that's as far as the theory will go. It doesn't deal with the details of how you find the minimum. It assumes this equation here and the preceding equations that we had here assumes that you find the global minimum. That's an assumption. How you find, or if you can find it, is not a concern. This is the theoretical setting that we have. But local minima do not enter the picture at all.
Can you use exact type of to state space or only approximate?
Yes, we can if we are lucky and we can execute the minimization. Now we're going to see an example, the linear quadratic example later in this lecture, where you can do it. It involves continuous control variables, and you can do the minimization exactly and in closed form. And there are a collection of good guys in dynamic programming, good problems, favorable problems for which you can find a closed form solution. If you have to find a solution computationally, and you have continuous control spaces, then inevitably you have to have approximations, because the computer cannot deal with continuous, this type of continuous minimization. Okay, so we are in the subject of approximation value space. The question is, how do we find this J tildes here? And I'm going to illustrate the case of rollout, which is an algorithm that we're going to be using quite a bit. Okay, so here we're dealing with a discrete control space, a finite number of controls. And we're going to do the optimal cost approximation. We're going to replace the optimal cost function with a cost function of some heuristic, the cost obtained by some heuristic, which of course need not be optimal. So here's how we use rollout. Upon reaching the state xk, we consider all the possible controls that can be used at that state. And ideally, we would like to have the optimal cost going from xk plus 1 to the end. However, instead of that, we run some heuristic that generates states from xk plus 1 to the end. And we take this cost, which we call xk plus 1 of hk plus 1, the heuristic cost, we take it as a substitute for the optimal cost. And this is our approximation. Our J tilde is this h here, generated by some heuristic. And once we calculate all of these heuristic values, which are really like approximate or heuristic Q factors, right? We use, okay, it's cost of the first stage plus the heuristic cost is a heuristic Q factor, you might say. Then you apply the U tilde k that minimizes this. So we calculate this, and we apply the U that gives you the minimum approximate Q factor. And then we generate the next state. We go from xk to xk plus 1. Let's save this. Go to xk plus 1. Do the same thing. Consider all controls, approximate the optimal cost with the cost of a heuristic, and go forward from x0 all the way to the end. Okay? So let me illustrate this with a traveling salesman problem like the one that you had in your homework. It involves 4 cities, A, B, C, D, The problem is specified by this matrix of intercity travel costs. So to go from A to B, it's 5. To go from A to C is 1, and so on. And these travel costs are the black numbers that you see on the branches. And you can solve the problem exactly by dynamic programming, as we know. And the optimal cost to go numbers are these red numbers that you see here. And suppose now that we want to apply rollout with a base heuristic, which is very simple. It's the nearest neighbor heuristic. From a given city, you go to the nearest city that you can go to in one hop, okay? So if you are in city B, then you would go to city C because that's the minimum one, okay? The nearest one. So here's a schematic of the rollout. We are at xk. A state xk is a partial tour, okay? A number of cities without that don't close a full tour. And then we consider all possible next cities. And then from each one of those, you run the nearest neighbor heuristic to complete the tour. So let's say we start at city A. What would the base heuristic do? Out of all these three, it will go to this one. Out of this one, out of these two that it can go, it will go to this one. Then there's only one to go and only one to go. So the base heuristic will generate from city A this trajectory here. It's not optimal, of course, right? The optimal happens to be this red one. And there is a way to calculate to apply the nearest neighbor heuristic from any partial tour. So from here, it will go to here, here, and so on. If you are here, it will go to here and here. If you are the nearest neighbor heuristic from here, it's going to go first to this one, then to this one, and to that, okay? So these numbers, the H numbers, are defined from every state. And we use those in place of the J stars. So let's apply a rollout in this problem. We start at the initial state, arbitrarily taking city A. We look at all possible controls, all possible choices, and we run the base heuristic from there. So from AB, we run the base heuristic, and we get a total cost of 27. 5 plus 1 plus 1 plus 20 is 27. And so that's the Q factor associated with this choice. Now from here, we have the base heuristic goes this way, and it has a Q factor of 28, right? From here, it goes for this choice, we go, the base heuristic will follow up with these cities, and it's going to be like 63. So we compare these three Q factors, and this one is the best. So rollout will move you from A to B and have this partial tour. Now we're going to do the next step. Consider the two possible choices and run the base heuristic from it. So this one will give 1 plus 21. This will give 4 plus 3 plus 1. So this one is the best one. And so the rollout algorithm will move from here to here. It will change trajectory, okay? We'll move here. And from here, of course, from this state, there's no choice, and we'll move to city C and so on. So look at what happened. We didn't look for the optimal that required all this gigantic calculation. We did a much simpler computation that's polynomial, actually, in the number of cities. And what we did is start out the base heuristic from the city A, and then the rollout algorithm generated a better trajectory. From 28, it reduced to 27. Then it changed its mind again and followed another trajectory with a cost of 13. And it so happens that here, this trajectory of the rollout is also optimal. That doesn't have to be, but we will see that rollout is very effective in improving a lot over the base heuristic. And the mechanism for doing this is we're going to explain in terms of Newton's method, something that's going to do in the future. But the thumbnails of this type of algorithm is, first of all, it's very fast relative to the optimum. Second, it works well. And the third, it can improve on any heuristic. No matter how good or bad heuristic, it can improve on it with relatively simple computation. So you're going to be asking your homework to do this computation for a bigger problem, and then we'll take it, and then you'll get a sense of what's involved. Are there any questions? Yes.
Exactly, how does rollout really improve on the baseline? Can you just tell me that? So for in this case, let's consider if the optimal cost was at 80, like it was the last node, and so in that case, it would go till the last iteration, right?
Let me interrupt you. I'm not going to go into the explanation of why it improves, okay? This requires a long explanation that lies further ahead. But it doesn't improve always because the base heuristic can be really crazy. It has to satisfy certain assumptions, but these assumptions are not overwhelmingly difficult. And even if you choose a stupid heuristic, there's a general method to make it improving by modifying it a little bit. Now, to explain this on this example, it would not help at this point. So be patient or read ahead in your textbook and you'll see the answer.
This method, it works like it can turn out different results based on different heuristic costs.
Yes, sure. Yeah, what you get depends on the heuristic that you use.
Okay, so if there are kind of like hyperparameter-tuning way to find out the best heuristic cost estimation.
Okay. Usually you pick heuristics on the basis of convenience, what's available to you. And you can try them out, all of them, or most of them, and see what happens, which one works better. You can also combine them all together and get something that's better than all of them. You get a rollout algorithm that performs better than all of the heuristics together. And we're going to explain how this is done 3 lectures from now or so. And the other thing that's going to come out again from future lectures is that the quality of the base heuristic does not matter all that much. And you can have heuristics that are far apart in terms of effectiveness on their own, but if you roll them out, you get results that are pretty similar. And that's going to be explained in terms of the Newton method interpretation that we're going to discuss starting from next lecture. Okay. So let's go into stochastic dynamic programming. So we generalize our problem to introduce stochastic uncertainty. Again, we have a system that generates states over n stages from x0 to xn. The transition from a state xk to the next state xk plus 1 is governed by an equation that depends on control, but also depends on a random disturbance, wk, some uncertain parameter, which may vary depending on the context. The practical context could be physical noise in an electrical system, could be in an investment problem, it could be uncertainties about stock prices, demand for inventory, breaking down machines unpredictably. Any kind of stochastic uncertainty is allowed here in principle. So the next state is not determined by the choice of control. All we can say is that we can have a probability distribution over the next states, which is determined by the probability distribution of this random parameter. There's also a cost function. There's a cost that depends again on the random disturbance, as we call it. the W. And the cost is the cumulative sum of the plus a terminal cost like before, but there's a difference here. This is not a number, but rather it's a random variable, right? Because W is random and also the states are random. So to get a number here that will characterize the performance of a sequence of controls, we need to take the expected value. Expected value, that is the weighted sum of the values of this cost weighted by the corresponding probabilities. So that's our cost function. Now, here's another thing about stochastic problems. We have to look at policies. Policies are not sequences of controls, but rather sequences of functions of controls, which we call mu0, mu1, all the way to mu(n minus 1). These functions determine the control that you are going to apply at a given state. So you can view mu(k) as a lookup table, which gives you what control to apply at state xk. So we have a different control for each different state, which is given by this function mu(k). Now, why is that? As the system progresses, we land at different states, and it would not be a good idea to apply the same control at all states, which we can predict at the initial state, but rather it would be helpful to wait to see what state we get and choose the control accordingly. So that's the consequence of this stochasticity. We don't know exactly where we're going to land when we get a control sequence, and therefore we need to wait to see which state we're going to be in. This is called a feedback policy or a closed loop control law. And the preceding one that we had for deterministic problems was called an open loop control sequence. Now, for deterministic problems, open loop control sequence and closed loop control laws give you the same result. If you optimize over one, you get the same result as if you optimize over the other. But for stochastic problems, it makes a genuine difference to have feedback, to have a closed loop policy as opposed to an open loop control sequence. So we have to minimize over these more complicated objects. And like I said, the important point is by using feedback, choosing controls with knowledge of the state is beneficial in view of the stochastic nature of the problem. So now if I give you an initial state and I give you a policy, these costs are defined as numbers, which are random, however, because of W. Taking the expected values of those gives me the cost of the policy starting at an initial state x0. So this is a function of the initial state and depends on the policy. And the optimal cost is obtained by minimizing over all policies of this j pi's of x0. And this is j star, the optimal value of the problem, and depends on the initial state like it did for deterministic dynamic programming problems. And of course, an optimal policy is one that attains the minimum in this minimization. Now, what we're going to do is extend the dynamic programming algorithm to this setting. Questions here?
So, why we don't have like one policy function, like that's mu1 and mu minus 1, they all don't take any input for just
you can think of situations where the controls that you would apply when you're close to the end would be different than the cost that you would apply at the same state, but in the beginning.
But the input is still like just a stage, right? So consider the chess positions. Like you put like occupy like one position, the policy should be The stationary.
Okay. Okay, we'll see later that for infinite horizon problems, where your position, no matter how many stages you have played already, what stage you are, the future looks the same. So in that case, stationary policies that do not depend on the stage, but only on the state, make sense because the tail subproblem looks the same. It goes from the current state to infinity. So what happened before or how many stages you were doesn't matter. And on the other hand, if you have a finite horizon problem, look, for example, suppose that you have to exercise an option. You have bought an option in the stock market and you have to exercise it, and you have to exercise in 30 days. Your exercise policy is going to be different one day from the end than 20 days from the end, okay? Even if the price of the stock is the same.
So it's like the fewer days you have, you want to be more conservative. So that's why.
And that will change your mu. Okay, let's go into the dynamic programming algorithm. Like the deterministic case, it produces the optimal cost of the tail subproblems that start at xk at stage k. All of those, it solves all of those. And it starts with the final one that's defined by the terminal cost function, then goes to time n-1, and it uses a formula that's pretty much like the one of the deterministic case. It minimizes overall possible controls, the cost of the current stage, plus the cost of the remaining stages, assuming that we act optimally. However, this number here is random because of the dependence on W, so we take the expected value. And the intuition behind that is pretty similar to the one that we use for deterministic problems, and the mathematical derivation is not so much more difficult. So it makes sense intuitively, and we're going to leave it at that. This is the way the algorithm is. And it works similar to the deterministic case. We start at the end, go to stage n-1, n-2, and so on, up until we get to stage 0. At that point, we will have obtained the optimal cost function. Now, in the process of doing this calculation backwards, we can calculate the optimal control at every possible state that can be encountered, and we can construct the optimal policy by putting together all these states. On the other hand, it's also possible to implement the optimal policy online by going forward, starting at the initial state, observe that state, and do this calculation, go to the next state and do this calculation again, and so on. Now, so this is the difference between offline training and online play implementation using the results of offline training. And now there are some big issues here. We need to calculate J star. This is a formidable calculation. As was mentioned earlier, in the case where the state space is continuous, it cannot be done unless you're lucky to have a closed form solution. It cannot be done computationally. Even for discrete problems, they may be a very large number of states. This calculation is formidable. It's more difficult than in the case of deterministic dynamic programming because we have to compute this extra expectation. And that's not necessarily an easy calculation. Besides, you have to do it for every state and for every control, right? And then you have to do this minimization over all the use, which is in itself may be a difficult problem. So that's where reinforcement learning comes in and tries to simplify this difficult calculations. But before we go into approximation, value space, and reinforcement learning, let's look at an example where the structure is so favorable that we can obtain the optimal solution analytically. Okay, this is an important problem. It involves a linear system and a quadratic cost function. The system is linear in the following sense. I'm giving here the one-dimensional case, the case where the state is just a scalar. In general, this analysis extends to the case where xk is a vector with n components. And the new state is given as the summation of a linear a multiple of the current state plus a multiple of the control and a random disturbance, W. A and B are known, are given scalars, and I'm going to assume here that the W has zero mean. So that's the system, and the cost of each stage is quadratic. Q and R are given positive scalars. This is the cost on the state and the cost on the control at stage K. It penalizes deviations from zero. It encodes our desire to keep the state close to zero. And this part here encodes our desire to keep the control near zero. So we want to keep the state near zero with relatively small energy, so to speak. Q and R are given. They could depend on the state, but I have simplified here to make them the same for every stage. And there's a terminal cost, which is also quadratic. Okay, so that defines the problem. And the dynamic programming algorithm starts with the terminal cost and generates backwards Jn minus 1 star, Jn minus 2 star, and so on, according to the usual formula, the sum of the cost of the stage plus the optimal cost to go from the next state. The next state is this one. And we take expected value of that with respect to W, and we minimize over U. And the main result here is that this algorithm can be carried out in closed form and yields optimal costs to go of the following form: quadratic, with Kk being some number that can be computed in closed form, plus a constant. And constants, of course, don't bother us because they get outside the minimization. So essentially, the optimal cost to go is quadratic. And moreover, the optimal policy is linear in the state. It's proportional to the state, with Lk being some control coefficient that can, again, be computed in closed form. A very favorable result, and the calculation is not difficult. There's another thing that's nice here. The optimal policy does not depend on the distribution of Wk, as long as it has zero mean. Depends only on the mean, actually, of the distribution. But here we assume that zero mean, and what we get is basically the same result for deterministic, the same controller for deterministic problems or for stochastic problems. We get the same result for the case where there is uncertainty with zero mean, and for the case where there is no uncertainty at all. It's the same policy. This is called certainty equivalence. And for linear quadratic problems, it holds exactly. In other contexts, we may wish to use it as an approximation idea. Moreover, as I mentioned earlier, this result generalized to multidimensional linear quadratic problems where A is a matrix, B is also a matrix, and the vector X is a multidimensional vector, and similarly, UK is a multidimensional vector. All the calculations I'm going to show you generalize, except that they have to be done with linear algebra, with matrix algebra. This is possible to do. It's the kind of calculation that that when you take a course in control theory, you learn right away. It's a very fundamental kind of calculation in control theory. So what I'd like to do is apply this dynamic programming algorithm and show you how we obtain this result. Okay, so we're going to do it starting from the terminal cost, which is this quadratic. And then we're going to do this calculation of dynamic programming, and we're going to show that it gives you a quadratic again. So from quadratic, we're going to get a quadratic, and we're going to continue to get optimal costs to go that are quadratic. So let's see how this is done. Let's look at this long expression here. Xn minus 1 is fixed. The variable over which we minimize is u, okay? There's a quadratic here, and there's a function, a quadratic function of something that's linear in u. So this is quadratic in u. And we can expand out this quadratic, okay? Jn star is given by this expression. So here it is over here. We expand this quadratic into the quadratic of the first two terms, and then the quadratic of w, and we take the expected value inside here, and then the cross term between these two, take the expected value. This does not have any uncertainty, does not depend on w, but this is the expected value of wn minus f, which is 0. So this term here disappears, and this term here is constant. So let's do the minimization. We take out the terms that do not depend on u because they don't enter the minimization. So out goes this term. This term is q times the expected value of wn n minus 1 squared. So it's the variance of w, which I call sigma squared. It's a constant term. And what's left is this quadratic minimization. Now we know how to minimize quadratics. Take the derivative and set the derivative to 0. It's a positive quadratic. It's not a negative quadratic. It's a positive quadratic. So it admits a global minimum. Setting the derivative of this to 0, all these quadratic terms, gives you this. And this equation can be solved for u. And the solution is this. Okay, you have to calculate it. Take u to the one side and all the rest in the other side, and make a division, solve this equation, and what you get is a linear expression of x. Obviously linear. This equation shows a linear dependence between u and x, and the coefficient is this after you can see that by calculation. So that's the optimal policy for the last stage, n minus 1. It's linear, and after we plug it in here, this linear function of x, we're going to get something that's quadratic in x. And that quadratic is given by this formula here. Carry also this constant term. It is quadratic plus constant, with kn minus 1 given by this expression here, after some straightforward calculation. I'm not going to show you that calculation. But the main thing is that quadratic gives you a quadratic, and also linear control in the meantime. And we repeat this calculation again, from jn star n minus 1 to j star n minus 2. And we continue, and for every k, we get this general formula. Quadratic plus constant, with the k coefficients generated backwards according to this recursion, and the L coefficients, the control coefficients, depending on the corresponding k. Okay, compare these formulas here. We start with, we start with Q, and we generate Qn minus 1, and then Qn minus 2, and so on. And after we have all the k's, we also have all the L's. So that's the calculation, and you can do this calculation except in a more complicated way with matrices to obtain the generalization for the multidimensional linear quadratic problem. Questions here? Okay. So there are a lot of generalizations of this type of calculation in linear quadratic problems. We made this observation that the solution does not depend on the distribution of W, but only on the mean, which is 0 here, and we have a certainty equivalence. In other words, the stochastic problem can be replaced by a deterministic problem, and the optimal controller will not change. We talked about generalization to multidimensional problems. There's also a generalization to non-zero mean WK. Basically, you have to modify in a simple way the calculations of the previous slide. There's a generalization to infinite horizon. We're going to show this later in this lecture. There's also a more sweeping generalization to problems where the state is not known to the controller exactly at time k, but instead you obtain only some measurements, linear measurements of the state. And you accumulate those measurements and you can sort of infer somewhat inexactly of where the state is. And it turns out that the optimal policy involves an extended form of certainty equivalence. The optimal control that you apply at time k, given all the measurements that you have, is obtained by multiplying with this LK, not the state, but rather the expected state, given the measurements. Now, this expected state given the measurements is provided by an estimator. You estimate the state given the measurements. This estimator is the famous Kalman filter. All of this has a tremendous amount of theory behind it over a period of 60 years in control theory. And this is a remarkable result that certainty equivalence holds even in the case where you have partial observation of the state. Now, problems with partial observations of the state are called POM-DP in reinforcement learning and dynamic programming, partial observation Markovian decision problems. They're the most difficult problems that you can find in this entire field, and we're going to deal with them. We're going to mention them in the next lecture and also in subsequent lectures and see how we can deal with them. They're the most computationally difficult problems that you can find. But in the case of a linear quadratic problem, they're not so difficult. They're given by a form of the optimal policy is given by a form of certain equivalence. Now, like I said, linear quadratic problems are foundational in control system design, and they are the starting point for other lines of investigations and approximations. Problems with constraints. The linear quadratic problem in its pure form does not involve any state constraints or control constraints. But these constraints arise very often in practice: self-driving cars, model predictive control, chemical process control. And again, the linear quadratic problem comes into play through approximations in this type of design methodologies. State constraints as well as control constraints. The most difficult type of problem, where also linear quadratic problems play a role, is when the parameters of the system are either unknown or change over time, like the A and B coefficients change, and the controls and the constraints also change. This is a subject in the field of adaptive control. Again, linear quadratic formulations and the results play a role, but these problems are very difficult, almost impossible to solve exactly, even for the simplest cases. Approximations are needed, and the investigations have been going on in this area since the 60s. In reinforcement learning, these problems are also of great interest from the artificial intelligence point of view. And we're going to try to follow a common line of analysis and a common conceptual framework for both the type of problems that are used, that are addressed in control theory and in artificial intelligence. Any questions? Okay. So now let's go to approximation in value space, which is a very basic reinforcement learning approach that we're going to spend a lot of time with. The idea is very simple. We have dynamic programming that at a given state minimizes the sum of the current stage cost and the optimal cost to go from the next state. In approximation in value space, we approximate the value of this optimal cost to go with some approximate cost, J tilde. We replace J star with J tilde. That's what approximation value space is. And notice that, this is a method that's suitable for online play. Once I give you the J tildes, we go forward by minimizing in this way. And notice that, in addition to this approximation, there are some other difficulties. We have an expected value here, which can be very time consuming, and that can be approximated also by some kind of more easily computed approximate expected value. For example, if this expected value is computed by simulation, Monte Carlo simulation, you may consider to limited simulation, or even approximation of this W by some typical value, a form of certainty equivalence. This minimization can also be difficult, so you may consider some kind of simplification in the minimization. It's another form of approximation. There are three approximations: cost approximation, expected value approximation, for stochastic problems, of course, and minimization simplification. And all of this can be combined more or less independently of each other. And the art and the practice of reinforcement learning, to a large extent, has to do with different methods for dealing with all these three approximations. Now, a major variation is multi-step look ahead. This uses single step look ahead, one step ahead and then approximation of the future. Multi-step look ahead involves looking forward for multiple steps and then approximate the future with this J tilde. In other words, instead of considering this problem here, we'll consider this problem that involves the sum of the cost of the first L steps and then the cost of the future as measured by J tilde. Now, this is an L-step problem. It's not a one-step minimization. It's an L-step problem, which is itself a dynamic programming problem with horizon that is simpler, that's smaller than N. So that's what we gain. And you minimize over a policy, the control of the first stage, plus control functions for the remaining L-1 stages. And then what you will obtain is something that involves the first control and the remaining control functions, but you keep and apply only the first control, and you throw all of this away. Once you do this minimization, you apply UK, then you get to go to the next state, do this minimization again, you get a multi-step policy, throw away everything except for the very first step, then go forward again, and so on. So the calculation is longer. There's a lot more computational overhead in this minimization than in this minimization. On the other hand, generally speaking, with multi-step look ahead, you can get enhanced performance of the policy, of the look ahead policy that you get. So that's the trade-off. More computation for better performance. And in practice, you'd like to use as much look ahead as you can, except that you typically have a budget constraint because this is an online computation. And what ordinarily you would do is use as long as you look ahead as you can, given the computational budget that you can afford. For example, you may have to produce a control within the next 10 seconds. So you'll use as much look ahead as you can deal with in 10 seconds. But you may also have like 1 hour, or you may have half a day, in which case you can use longer look ahead. That's recommended. Now, in multi-step look ahead, we also have the 3 approximations. There's cost to go approximation, expected value approximation, and approximate minimization here. So that's the landscape of approximation value space, and that's where we're going to be dealing with for about 90% of the course. Various ways to do these 3 approximations in various contexts. Okay, let me go to the next slide, and then you can ask questions. Here's a bird's eye view of different ways to construct approximations. When it comes to approximation of J tilde approximation, there are many different ways to do it. One possibility is problem approximation. Solve exactly or almost exactly a similar problem that is simpler, and use the cost function of the similar problem in place of the used as J tilde. Certainty equivalence is a type of problem approximation where you replace a stochastic problem with a deterministic one, which is easier. There's another type of approximation called aggregation that we are going to discuss near the end of this class, which replaces the original problem with a problem of smaller dimension. It aggregates dimension, aggregates variables, creates a simpler problem, which it solves exactly, and then it uses its optimal cost function as J tilde. We mentioned rollout. Model predictive control also involves special types of J tildes. Parametric approximation in neural networks is a major one. You generate data of optimal or almost optimal cost, and you approximate it with you learn this cost function by using a neural network. We're going to see also, okay, so these are the major ones, and some other ones that combine various versions of, combine various components of different approaches, and that gives you just a partial list. Approximating expected values, an important approach is to use adaptive simulation. In many reinforcement learning contexts, you would calculate this expected value by Monte Carlo simulation. And you can do exact Monte Carlo simulation with a lot of samples, or not so exact with relatively few samples. That's what I mean by adaptive simulation. For some controls, you do a lot of simulations. For other controls, not so much. And how do you decide? Well, you would want to do accurate Monte Carlo simulation for the most promising controls. For the ones that, based on a few samples, they don't look very good, you don't want to bother with them too much. That's also the idea that underlines a popular approach in artificial intelligence called Monte Carlo tree search. Monte Carlo tree search is a form of adaptive simulation. Here, approximate minimization. You may have a continuous state space you approximate by a discrete, or you have a continuous space with a discrete space with a lot of components, with a lot of elements. You approximate it with fewer components. Like you have a fine grid, you approximate with a coarse grid, and then you may, on the basis of some criteria, thin out the control constraint set and pick out the most promising controls according to some heuristic criterion. That will simplify this minimization. All of these tricks are part and parcel of the methodology of approximation in value space. And this can apply to both one-step look ahead and multi-step look ahead. We're going to talk about all of this at one time or another in various contexts. let me give you also an examples of rollout. Rollout from a given state simulates a heuristic all the way to the very end. But one approach might be to simulate a heuristic for just a few steps and then take a cost function approximation after that. This is called truncated rollout and operates like I'm showing here. At a given state, I calculate all the possible next states, both for a deterministic context and a stochastic context, all the states xk plus 1 that can happen. Then you roll out with some base policy for a number of steps, m steps, a truncated horizon, and then you take a cost function approximation to approximate the cost of the remaining stages. And the base policy can be computed, can be obtained very easily. It may be a heuristic, it may be obtained through a neural network. And the cost function approximation, again, may be obtained in different ways. Problem approximation, neural networks, aggregation, and so on. So now, if you remember from the previous lecture, we gave a figure for alpha 0. It involved truncated rollout of this form, but also with multi-step look ahead. There's multi-step look ahead minimization version of this figure as well. And this is the alpha 0 architecture. Okay, so I think we are due to take a break here. Are there any questions? Yeah.
You re-explain what's the difference between offline training, because both stages you change the value functions, right? And it seems like online play you have limited resources. Is that the weakness or?
Online play means in real time. You control the system in real time.
Yeah. So
Offline play, it can be a week earlier, but
okay,
you do all the
so
calculations.
it's just the amount of computational resources for time.
Online play is real time. So if real time imposes you tight resources, that certainly will affect the kind of algorithm that you will use. Yeah. Online play is like you play chess. You play chess in real time. You move and then you move again and so on. Whereas offline training is DeepMind uses zillions of GPUs to calculate the cost function over a period of weeks and months. So, okay.
But it seems like judging on the name, it feels like online play doesn't change the value function or doesn't learn at all. But actually, you change the value function as well. For example,
Online play does not learn anything.
oh, really? Because when you said like you have a heuristic, you roll out with a heuristic, you compare like the cost of the choices plus the state that you end up with after you choose that action, and you compare it and then change the policy. So that's not.
Don't change the policy. You simply determine the control on the basis of calculations, but you don't learn anything. Okay, you don't learn a cost function. You just calculate the cost function. Okay, we're falling into the trap of semantics around the meaning of learning. What is learning? Okay, if I calculate 1 + 1 = 2, do I learn how to do 1 + 1, or is it just I'm doing addition? Different people mean different things with the term learning, and rolling with a heuristic which is fixed does not involve learning. Although you might say, I learned the cost of the heuristic, but that's not what I mean.
Okay, so my question is, in the stochastic variant, we brought in something called policies, but in the deterministic one, we just have states controls. So can't we just, in the stochastic case, to use noise variables, controls, and states to solve the minimization? What was the need for the lookup table for policies? I don't think I got it. Policies, what a policy is.
What a policy is?
Yeah.
It's a table. On one side you have states, on the other side you have controls. And in for every state, it's a prescription of which control out of the many you're going to apply at that state.
Start executing a policy, you may not like necessarily arrive at the state that you thought you were trying to arrive at by executing that. So because of that, you need a lookup table to figure out what to do in which state as you're evolving through the system. Because you don't know exactly what state you're going to arrive at. You simply execute the policy at that state, but there may be some stochasticity at which state you arrive at next, given that action. Does that make sense?
Okay, thanks, Jameson. Okay, guys. Yeah.
With one, hello. When you say finite horizon, do you mean that there exists an n at which point every sequence is terminated, or do you mean that like there are no non-terminating policies?
When I say finite horizon, I mean that you have to terminate at that time, and you cannot terminate earlier or later.
Okay, so every every sequence is the exact same.
So, yeah, right, yeah.
Okay.
Of course, in a reformulation of the problem, you can terminate early if you want, but then you have to introduce an additional termination state, and then you fill up the horizon by just staying in that state. Okay, so there's, as long as the horizon is as long as the horizon is finite, whether it's variable or not variable, you can always make it fixed.
My question was, on what basis do we decide the next L action for multi-step L lookup?
How do you design the parameter L in the multi-step look ahead? At what point? What do you mean?
How do we decide which action to take for the next L multi-step lookup? I mean, what policies to take?
Okay, so this is the figure for multi-step look ahead. So at state xk, you do this minimization, and you get this multi-step policy. You use the first term, and you throw away the rest. Now, the next step, you redo this minimization, but advanced by one time unit.
In this minimization, we are deciding UK based on the thing that gives us the minimum score for overall equation, right? But how we are deciding UK plus one?
UK plus one. So yeah,
UK plus one.
after you do the minimization, how to decide next based on
Well, this minimization is only for UK to decide what UK you're going to apply. After you move to the next state, it's an entirely different calculation. Has nothing to do with the previous one. You just redo the calculation with the new at the new state. And there's a good reason for that, because these controls are not useful anymore. You have moved with under uncertainty because of the W's, and they're not useful anymore. So you have to redo the calculation with new data. Yeah.
I mean, I understand that the question is how to do minimization over UK and also the subsequent policies. I think that's the intention.
Is this the question?
Yeah.
Well, it's a dynamic programming problem involving this terminal cost and this cost per stage. So you do it by dynamic programming, except it's a smaller horizon. This is also a dynamic programming problem of horizon 1. This is a dynamic programming problem of horizon L. I'm not saying that this is an easy calculation, but it's easier than the original problem. Plus, you can also do simplifications here, which will make it easier, even easier. Okay, I'm sorry, I didn't understand your question. If you are far away, my hearing is not perfect, okay? And if you're far away, it makes it more difficult, so please speak up a little louder. Okay, guys, so it's time to take this break. And we'll get back at 6:06. Okay, so now we're going to go into approximation in policy space, which is the major alternative to approximation in value space. In approximation value space, we approximate cost functions, value functions. Here we approximate policies, and we select a policy by optimization over a suitably restricted class of policies. Usually that class involves a parametric family of policies. In other words, the policies here do not depend on the state, but also depend on a parameter, which is tunable. We learn that parameter through data, most likely. So we look at a parametric family of some form, like, for example, the one provided by a neural network. R here in that context is a set of weights of the neural network. So for a given parameter, this controller goes into this feedback loop, observes the state, generates controls, and the system keeps going. So if you select a parameter, you select the controller, and therefore there is a cost function that's associated with that controller. And what you'd like to do is optimize with respect to the parameters, the performance of this closed loop system. This system depends on the parameter, and its trajectories depend on the parameter. You optimize the parameters, you optimize the system. Okay, so now this minimization in the space of parameters, and you can use many different methods for this optimization. Random search. Start with a parameter vector, simulate the controller, and based on the results, you move to another parameter vector, and then to another parameter vector through some kind of a random search mechanism. Now, I'm not saying that this is a good idea, but I'm just telling you that it's a possibility. An important class of methods is policy gradient methods, where you move this parameter in the direction of some gradient of cost improvement. Okay, there's a lot of literature in this field, and we're going to cover methods like that late in the course. There are also machine learning type of algorithms based on classification, which can be used for approximation in value space. We're going to talk about those late in the course. It's important to realize that this is not an online method. It's not used in real time. It's used offline. You train a policy offline, and then you use it in real time, but it has an important advantage then. Once you have calculated the parameters, this controller will spit out controls very quickly. You observe the state, goes through this neural network, the answer is immediate. It calculates the control almost instantaneously. Whereas, if you compare this with approximation value space, in approximation value space, you have to do a lot more computation online. So that's the great advantage of approximation in policy space, but there's also a disadvantage. Once you choose a parameter, you're stuck with it. If the problem changes on you, like for example, an unexpected obstacle appears in front of a car, a self-driving car, your controller has not accounted for that. If the conditions change, the problem changes on you, this approach does not allow for online replanning. And we will see also that from a theoretical point of view, it does not involve a Newton step, which we have mentioned earlier. We're going to discuss this later. Okay, so how do these so we talked about the major conceptual difference between approximation in value space and policy space. And approximation in value space, you have to do this calculation online. So it's an online play method. However, it can use the results of offline approximation policy space. Within this figure, it can use an offline trained policy for rollout. So that's where approximation in a policy space can be combined with approximation in value space. There's also the reverse. Given that you have done approximation in value space, you can go and do approximation in policy space to gain the advantage of fast response, of fast generation of controls. So suppose that you have obtained approximate cost functions J tilde. These define a suboptimal policy through one-step or multi-step look-ahead minimization. So given this J tilde, this involves quite a bit of minimization to implement online the suboptimal policy. How can we simplify it? Well, here's the idea. We learn mu tilde through approximation in policy space, which is done offline. And how do we do that? This mu tilde, we use it to generate a training set of a large number of state and control pairs. So we generate a collection of representative states, a large number of them perhaps, and calculate the corresponding control that would be obtained by this one-step look-ahead policy. So we collect pairs like that, and we use them to match, we use them to learn a policy that replicates these pairs fairly closely. So for example, we introduce a parametric family of policies, and then we calculate the parameters by some sort of least squares fit. So match an element, a member of this parametric family with the pairs of the training set through a least squares minimization. Note that all of this is done offline and all of this is done offline. But if you get this policy here, this train policy, it gives you answers much more quickly than this minimization does. So you can view this as approximation in policy space on top of approximation in value space. Okay, are there any questions? In our course, we're going to focus on approximation in value space to a great extent. Methods for approximation in policy space are going to take about a lecture or maybe a lecture and a half near the end. That's part also of my bias. I think that approximation in value space is a more interesting and a more efficient and effective type of method than approximation in policy space. Okay, so now let's go into infinite horizon problems. We're going to do an overview. There's a lot of theory associated with infinite horizon problems, some of it quite mathematical, but we're not going to get into that as much here, and particularly in today's lecture, it's only going to be an overview. So what's the infinite horizon problem that we're going to be discussing? It's like the stochastic dynamic programming problem over a finite horizon, except that the number of stages is infinite. The control goes on for an infinite number of stages. There is a system involved here. The system is stationary. F does not depend on K. That's important in infinite horizon problems. And we consider again policies, one policy, one control function for every stage. And the cost of each stage is determined by a function G that is similar to the finite horizon case, but is also weighted by some alpha to the K. Now, alpha is a scalar between 0 and 1. And if alpha is less than 1, this alpha to the K is proportionally small and specifies that costs occurred far into the future do not count as much as costs at the same state earlier in the horizon. So costs diminish over time due to this discount factor. And this has interesting mathematical ramifications because it makes the cost, it keeps the cost finite. So the cost doesn't explode through accumulation of these terms G. So let's see what's the cost function is. It is the n stage cost with n going to infinity, but it includes also this alpha to the k. As a result, if G is bounded, this expression remains bounded because it involves the sum of a geometric progression multiplied with bounded terms. It's finite, okay, mathematically speaking. So the cost function is finite. The cost at a given, starting at a given state of a given policy is finite over an infinite number of stages in this case. And that gives rise to the nicest class of infinite horizon problems, which are called discounted. They involve a discount that's less than 1 and a cost per stage that is bounded. The optimal cost function, of course, is given by minimization of this expression. There are also interesting problems where alpha is equal to 1, but they typically involve a special termination state. And once you reach that termination state, which may happen at a random time, the cost accumulation stops. So you guarantee finiteness of the cost through this termination state. And in this case, the objective is to reach the termination state at minimum expected cost. The most common and easiest to understand infinite horizon problem involving a termination state is a shortest path problem. In a shortest path problem, you want to reach some destination and then cost stops accumulating after you do that. However, it's also possible to view it as an infinite horizon problem where you sort of spin around cycles before you go to the termination state. And however, it's an example of a problem where some policies have infinite cost. However, the optimal policy always has final cost as long as there is a path from every state to the destination. Shortest path problems, deterministic shortest path problems are a special case of this, but there are other problems called stochastic shortest path problems that involve stochastic uncertainty and are more complicated, but very useful in practice because problems with termination states arise often in applications. In our presentation, we're going to focus on the easiest case, which has a nice theory, discounted problems. We're going to touch upon stochastic shortest path problems a little bit here and there. Now, are there any questions about the formulation? Okay, there's analytical theory and computational theory. There are 3 theorems in infinite horizon problems that you aspire to prove. You hope that they hold in your given in a given problem setting. The first theorem says that the k stages optimal cost converges to the infinite horizon cost as the horizon goes to infinity. In other words, if you take a finite horizon problem with the same cost and with the same cost function, then if you let the horizon go to infinity, in the limit, you're going to obtain the infinite horizon problem and therefore the infinite horizon cost. That makes sense. And mathematically, it says that J star is equal to the limit of J case of X, where J case of X is the optimal cost starting from X and going for K stages forward. Now, this JK function is generated sequentially by this formula. Okay, look at this formula. It says that the cost over K stages, optimal cost, is obtained by minimizing the sum of the cost of the first stage plus the sum of the cost of the remaining stages, but starting one step later and therefore discounted by an additional alpha term here. Okay, that's where alpha, the discount factor, comes in. Now, intuitively, this makes sense. Mathematically, there's a simple derivation based on dynamic programming that you can read. I'm not going to let me not go through it. So you solve the finite horizon problem for one step horizon, then 2 steps horizon, 3 steps horizon, and so on. But you don't need to resolve from the beginning. You just do this simpler iteration to generate all the finite horizon costs. This is also called value iteration. It's an algorithm to calculate in the limit J star. So that's the first theorem. Second theorem is Bellman's equation. Bellman's equation holds that J star satisfies this equation. Given this formula here, and assuming that you have this, that J star is the limit of the J case, take the limit of both sides here. On the left side, you're going to get J star. On the right side, assuming that you can get the limit inside, you get the limit of Jk minus 1, which is also J star. So this is what you obtain. Okay, this equation, I've sort of hand-waved here with limits and so on, but it turns out that it holds just about always in infinite horizon dynamic programming. It's one of the most reliable results. This one is not so reliable as this one. So we're going to take it as given that J star satisfies Bellman's equation. And for discounted problems, it turns out that it's the unique solution of Bellman's equation. Notice it's a functional equation. The unknowns here are the J star functions. In the case where X takes a finite number of only a finite number of states, let's say n states, then J star is an n-dimensional vector. So this becomes an n-dimensional vector equation, which is nonlinear because of this minimization. This is the most fundamental object in infinite horizon dynamic programming. And the objective is to find this J star or to approximate it by using reinforcement learning techniques. So theorem number 1, theorem number 2, theorem number 3 says that if you manage to solve Bellman's equation and have J star, then by minimizing on the right-hand side, you obtain an optimal policy. If mu stars of X depends on X, attains the minimum in Bellman equation, then the function that you obtain of X gives you an optimal policy, which is stationary. It doesn't depend, the control that you apply depends only on the state and not on the stage that you're in. One nice thing about infinite horizon problems is that optimal policies generally are stationary, and you can restrict attention to stationary policies, which involves a smaller number of values, right? It doesn't depend on the stage. It only depends on the state. So these are the 3 theorems. And there are also 2 algorithms here, 2 main algorithms. One is called value iteration, and the other one is called policy iteration. Both of them are very important and have reinforcement learning analogs. In value iteration, we generate a sequence of cost functions, each one being the optimal cost function of a finite horizon problem. It's the same equation I gave in the previous slide, except that the initial J0 is not 0, but rather can be arbitrary. I have a question mark here because there are some theoretical issues around this assertion. But that's the algorithm. Start with some J0, generate J1, J2, J3, and so on. And in the limit, you hope to get the optimal cost J star. The other algorithm is policy iteration. Instead of generating a sequence of optimal cost functions, it generates a sequence of policies and their cost functions, starting from some more or less arbitrary policy. And the typical iteration starts with a policy and generates a new policy in 2 steps. I gave this algorithm in the context of AlphaZero. This is the AlphaZero algorithm, TD-Gammon algorithm, except with approximations. That's 2 steps are policy evaluation. We compute the cost function of this policy, which I generally refer to as base policy. And then the new policy is obtained by policy improvement, which computes the improved policy, a rollout policy, so to speak, by using the 1-step look-ahead minimization. So start with mu0, evaluate it, improve it to get mu1, evaluate mu1, improve it, and so on. And we keep going. And let me also mention that this policy evaluation step, this J-mu, can be done in a number of ways. You have to solve basically this Bellman equation, but for the policy, without the minimization, and the control substituted with mus of x. And you can do it either using value iteration without this minimization, or you can use some other method. And one nice thing about this equation is that it is linear in J. If J is a vector, an n-dimensional vector, this is a matrix equation, a linear equation that can be solved by Gaussian elimination, MATLAB. So there is this possibility for policy evaluation. Another possibility is to calculate the cost of a policy by just simulating it and doing Monte Carlo simulations starting from different states. That will also give you values of the policy for these initial states. All of this is very basic, and all of this involves a lot of approximations that are central to reinforcement learning. So let me give you a schematic diagram here. This is exact policy iteration. Given a policy, the base policy, you evaluate it, calculate J-mu, then you improve it by minimizing Bellman's equation with J-mu instead of J-star. That gives you the new policy, and you keep doing the same thing over and over. That's policy iteration. And some of the important facts are you expect that policy iteration will give you in the limit an optimal policy. This is true for easy problems. For more difficult problems, there may be some question marks about it. It's an important question to ask here. We generally will assume that policy iteration does give you an optimal policy, particularly for discounted problems for which this can be proved mathematically. Policy iteration is much faster than value iteration. The reason is that it can be viewed as Newton's method for solving Bellman's equation. And Newton's method is much faster than the type of iteration involved in value iteration. And the factors of interest in reinforcement learning is that policy iteration can be implemented approximately. It's one of the most fundamental methods in reinforcement learning, approximate policy iteration. And the way you do that is by approximating these 2 steps with some kind of neural network, typically, a value and possibly a policy network. This is the type of algorithm that's being used in AlphaZero, TD-Gammon, and many, many other contexts. You have a policy, you generate data with this policy, and you approximate its value function. You obtain what's called a value network. Then you generate samples of improved policy, and you fit a policy network to that data. And then you obtain this new policy, and you keep going. So this is a framework that we're going to discuss in many different contexts, and also in limited forms. In particular, rollout is going to be viewed only one step of this loop here, not repeated generation of policies. Okay, so that's all I have to say for the moment for infinite horizon problems, but I would like to specialize this theory to linear quadratic problems, the same linear quadratic problem that we saw earlier in this lecture. Questions? Okay, linear quadratic problems in infinite horizon. We have the same system, and I will consider the deterministic case. Everything goes through for a stochastic problem, except that you have to use certainty equivalence for that and do a little bit more mathematics. So let's consider the deterministic problem, where the state is generated by a linear expression, linear on the state, linear on the control, and one-dimensional. The cost per stage is quadratic. This is Q and R are given positive numbers. The penalty on the state, we try to keep the state near zero, and the penalty on U, try to keep U small. And Bellman's equation is given by this expression, right? Minimization over first one stage cost plus cost of the future stages as measured by J. And we have to solve this Bellman equation. Now, J is a function of X, and it's not represented by a finite set of numbers, but it turns out that it is quadratic. And that allows us to solve this equation in essentially in closed form. Now, why would it be quadratic? We know that the K stage's optimal cost is quadratic with a cost coefficient case of K, which can be calculated with a recursion. So assuming that this K's converge to something as K goes to infinity, and that something is K star, by the value iteration theorem, we expect that the optimal cost of the linear quadratic problem is K star X squared. And we also expect that the optimal policy is going to be linear, where L star is obtained from this Bellman equation once we plug in K star. You plug in K star here, what you obtain is a quadratic minimization that can be done in closed form, and it gives you this expression here with L star calculated readily from this quadratic minimization. Okay, so let's see what's the form of K star and L star. We plug in this quadratic expression into Bellman's equation, and we obtain this, right? Now, this minimization is quadratic in U. It can be done in closed form. So after you do all that, and the type of take the derivative and set it to zero in the way that we have done in our earlier calculations, you obtain in the end that K is equal to this function here of K. K is equal to this expression here. So you have to find K such that f of K is equal to this. And also, once you find this K, the minimizing U obtained from this minimization, similar to our earlier calculations, is a linear function of K given by this expression here. So the final result is what you see here. The Bellman equation is solved by a quadratic function, with K star being a solution of this equation. This is the left-hand side of this equation. This is the right-hand side. This equation is called the Riccati equation. It's very fundamental in control theory. And it dates to the 1700s. Count Riccati was a count and also a famous mathematician in his day, and he invented this Riccati differential equation. And since that time, there has been a lot of work on this equation because it has some nice properties. And it's very fundamental in control theory because it arises in this linear quadratic problem. This is called the Riccati equation associated with the linear quadratic problem, but for the one-dimensional case. All the data of the problem come in here, A comes here, B comes here, R and Q. And I'll show you a graph of this Riccati equation shortly. Once you solve this Riccati equation and you calculate K star, then you can calculate the optimal policy according to this formula here. Find the control coefficient L star according to this, and the optimal control is a linear function of the state. It's proportional to the state with a factor of proportionality being this L star. Okay, so that's the solution. I hand-waved a great deal here based on the solution of the finite dimensional problem. And now let's see what kind of insight we can get into the solution of this Riccati equation. Are there any questions here? Okay. There are methods for solving Riccati equations that are very efficient and very inventive. However, we're going to use a graphical solution that provides a lot of insight. And we can do a graphical solution because we're dealing with a one-dimensional problem, and therefore K is a scalar as opposed to being a matrix. So here's the Riccati equation. K equals to F of K, with F being this expression. It's a function of K, nonlinear function, right? Because K also appears in the denominator here. And it involves A, B, R, and Q. And it has this form that you see here. It's a typical form of the Riccati, the right-hand side of the Riccati equation. I'm going to solve it graphically as follows. I'm going to plot F of K, the right-hand side, and I'm going to plot also the left-hand side, which is just a straight line, right? And the point where the two meet is the solution. You see this? Here's the right-hand side of Bellman's of the Riccati equation, and here's the left-hand side, which is just K. K as a function of K. This is a function of K, which okay. At the point where they meet is the solution K star. There's also another solution here, but that solution is negative because Q is positive. The crossing point is above zero. So we are only interested in the positive solution. Now the curve is concave. You can verify that. And also it approaches an asymptote at this point. Okay, so for K going to infinity, if you divide here by K, then what you obtain, then what you obtain is this value here. It's easy to verify that this is the correct asymptote. And there's also another asymptote where this red curve goes to minus infinity. When the denominator here becomes 0, this goes to F of K goes to minus infinity. So that's the graphical solution. And you can get a lot of insight from this graphical solution, which can be generalized to the multidimensional solution. Of course, you have to verify all the conclusions that you draw from the one-dimensional solution. You have to verify that it holds, that they hold for the multidimensional solution, do the mathematics and the proofs, and verify that indeed this is true. Now, this graph here can be used to understand value and policy iteration, and that's very important for our subject. because both value and policy iteration are important algorithms that we're going to use with approximations in reinforcement learning. We're also going to interpret reinforcement learning algorithms on the basis of graphs like this. And this is going to provide insight on what we're going to be doing. So here is value iteration. How does value iteration works? It generates a sequence of cost functions. And these cost functions are the optimal costs for the finite horizon problems of k+1 steps. We have shown that they are given by this expression here, with f being this function. So value iteration generates a sequence of quadratic functions where, however, the quadratic term can be canceled out, and you can write value iteration as an iteration on the cost coefficients. So this is basically a way to solve the Riccati equation by using value iteration. Generate a sequence of k's that converges to k star. Now let's plot this value iteration on this figure. The f function is this red function here. The typical iterate starts at k and calculates k+1. And here is k+1. It's obtained at the point where this vertical crosses the graph of f. Now, this k+1 plotted down to the k-axis is given here. And then k+2 is this level here. And it projected down on the horizontal axis is this. So value iteration can be visualized as a staircase iteration starting from some initial condition and generating an infinite number of iterates, which you can see from this figure, that converges to k star. No matter where you start here, the staircase iteration converges to k star. And even if you start on this side, again, the staircase iteration converges to this k star. And you can see also that the iteration can be fast, but it can also be slow, depending on the slope of this curve here. If it comes very close to being to the 45-degree line, then the progress is slow. Now, in the next lecture, we're going to visualize in the same way policy iteration. We're going to see that's much faster. And we're also going to see how approximate value iteration works, and also general approximation in value space works for linear quadratic problems using the same visualization. And this visualization is insightful, motivates several conjectures, and also generalizes to problems beyond the linear quadratic domain. It's based on ideas that are far more general than what you see here on this graph. But we're going to be drawing our insight primarily from this type of linear quadratic type of graphs. So that's my last technical slide. Are there any questions on this lecture? Okay, it's late. Yeah, please.
So when you have like a value network, automatically you can sort of deduct like a policy network, like a policy out of the value comparisons.
That's right. If you have a value network, you can do policy improvement, approximate policy improvement, get data, and construct a policy network.
Okay, so when you said you like policy, you don't like policy iterations, like value iterations more.
I said that?
Did I misheard?
No, he said that he doesn't like approximation in policy space as much as approximation in value space.
Okay.
Yeah,
So-
exactly. Thank you.
Yeah.
Thank you for corroborating.
So, where do you draw the line? Because when you approximate value space, automatically you get policy as well. Like, it seems like policy iterations, or policy method, its only merit is being fast. And like, I guess my question is not there. Can you just talk more about it?
Well, what I said is that approximation in policy space has the advantage that it's very fast online. It gives you controls in response to given states very quickly. But it has some major disadvantages. One disadvantage is that it's not suitable for online replanning. In other words, if the problem changes on you, some of the constraints change, some of the dynamics change, the A and B coefficients change, then you're stuck with whatever you've trained offline, and you can't change the parameters of your policy network in response. So it's not suitable at all for problems, for adaptive control problems, for example, because the problem changes on you, and you have trained on a different problem. It's like having trained on checkers, and then you are presented with a chessboard, which is you're being asked to play chess after having trained on checkers. And that's one disadvantage. Another disadvantage, which is more subtle and has to do with performance issues, that the ceiling on performance is lower for approximation in policy space. Even if you implement it perfectly, it will not do as well as approximation in value space under more or less similar circumstances. Now, that's harder to explain, but I hope that it can become evident as we go along in this course.
Thanks.
Along the same lines, are there ever scenarios where we would want to do both approximation in value space and approximation in policy space and have an approximate of each? Like for instance, if we wanted to do online replanning, but still have some kind of policy approximation, just because it's computationally faster. Is that something that's ever done?
Sure, yeah. AlphaZero uses two networks, a value and a policy network. And in the context of model predictive control, you can have an identification algorithm that identifies new dynamics as they change. And you can do your approximation in value space using the identified dynamics, the current dynamics that hold after the problem has been changed on you. But when it comes to rollout far into the future, you may use an offline trained policy.
Do you know when the dynamics change? Like what method is used specifically to identify that these dynamics are changing?
This is context dependent, depends on the context. You know, my self-driving car has cameras, okay? And the cameras presumably have algorithms that drive them and tell you when there's a person in front of the car.
And specifically, like, would we be able to tell, for example, if like a certain policy isn't working as well, would that be an indication that we should do online replanning, for instance?
This is entirely context dependent, depends on the problem. The dynamics, the changes in dynamics can be very, very different for different problems. It's hard to make general statements of that kind.
About the AlphaZero to networks thing, are those independently trained, or is like the policy one trained to imitate the value one?
In AlphaZero, they're trained together. They're trained together. And ordinarily, they would be trained differently. They could be trained entirely differently. So, I mean, they're trained on different data. The value network is trained on cost data. state cost pairs. The policy network is trained on something that's entirely different. It's trained control state pairs. Okay, so I mean, costs are one-dimensional. It's just a number. A control could be multidimensional, and the costs take continuous values. Controls may take the values from a finite set, a discrete set. So the value network and the policy network may be very different. And in alphas, in approximate policy iteration, they train sequentially. You first train one and then use the net from the value network to train the policy network.
Okay,
And
so
then-
you do use that value data. in
Yes,
order to
sequentially,
schedule.
but not together in one box, in one
Okay.
piece of software. Yeah, right. There is in synergy, certainly they are used in synergy. They're trained in synergy, yeah.
The follow-up question on the approximation in the value space, does it also suffer from the adaptive control issue?
Adaptive control?
That like the approximation in the value space, does it also suffer from the adaptive control? Because the approximation in policy space is suffers, right?
Yes. In approximation in value space, part of the computation is done offline to compute J tilde, the cost approximation, and part of it is part of the computation is done online. This one step or multi-step look ahead minimization. So the multi-step look ahead minimization can take into account the changed problem data. So if you have a system identification algorithm that identifies the new dynamics of the system, then this multi-step look ahead minimization will adapt to that, will take into account the new data. That's called online replanning. Now, the part that has been trained offline cannot be changed. There's just not enough time to change that. So, okay, that's, yes.
And also another on the policy network and the value network. So they are somehow like connected because the policy is the optimum of the minimum of the cost. But what if we train them separately? Will it break down the linkage between them? And then what if the linkage is broken? Then which one should we choose to guide the next state of next control?
Okay, the value networks. Okay, let me go back to the corresponding figure. Okay, so here's the figure. Okay, the value network is trained, and then the policy network is trained using the value network, okay? Because the value network is used to generate a new policy, and the new policy is generating the data that's training the policy network. So these computations are synergistic, but they're also sequential. And the inner structure of the value network may have nothing to do whatsoever with the inner structure of the policy network. I mean, this generates controls, which are multidimensional entities, whereas this generates values, which are one-dimensional and continuous. So definitely the structure of this should be different than this. And they're done in sequence also.
Thanks.
I'm glad that you asked me all these questions. I welcome this. We would like to go through reinforcement learning in 2.5 hours. But like I said, the first 4 lectures are an overview, and I have deliberately chosen to use I have deliberately adopted a fast pace, a very fast pace, so that I'm able to cover the broad picture in 4 lectures and to get you started in doing some targeted reading on different parts of the landscape. And after the 4th lecture, we're going to get into specific topics in greater detail. However, we're not going to be able to cover the entire landscape in depth. We're going to paint the broad picture and then focus on specific parts of that picture. And if you're not interested if your interests lie outside these parts, you have to do some reading of your own. For example, your term paper doesn't have to be on a subject that we have covered in depth here, but it's going to be up to you to read and to understand in greater depth the subject that you are interested in. Of course, we're going to be ready to help you with literature and suggestions if we can, because the field is so vast that I'm not sure that we understand it fully in all its depth and breadth. Okay, so I have another slide. Don't go away. About the next 2 lectures that will conclude our overview. We're going to cover these Newton step interpretations. We're going to focus on linear quadratic problems, but we are going to comment on how they extend beyond linear quadratic problems, basically by using the visualizations that I gave in the last 2 slides. The argument that we're going to make is that approximation in value space is a Newton step for solving the Riccati equation, or more generally the Bellman equation, starting from the cost approximation. As a special case, we're going to argue that rollout is a Newton step starting from the cost function of the base policy. And policy iteration is going to be a sequence of repeated rollouts and therefore a sequence of repeated Newton steps. That's going to be our conceptual framework, and we're going to illustrate it visually using linear quadratic problems. Then I'm going to take you on an overview journey over the different types of problems that people look at in dynamic programming and approximate dynamic programming and reinforcement learning. There's the issue of how do we formulate dynamic programming problems in practice. We're going to discuss problems involving a terminal state, such as stochastic shortest path problems that I alluded to. We're going to discuss a general technique called state augmentation that allows complicated problems to be reformulated in the format of the problem that we have considered. We're going to discuss POM-DP, imperfect state observation problems, multi-agent problems, which involve a control space that's very large because each control consists actually of many components, one component corresponding to a different agent. So if there are 200 agents, for example, in your problem, that control would involve the Cartesian product of these controls of the 200 agents. So it's going to be a very vast space of controls. And how do we deal with the computations associated with that? And we're going to talk also about adaptive control, as well as model predictive control for systems with unknown and changing parameters. So it's going to be an overview of the applications and the playing field. And I would urge you, as I have done in the previous lecture, that you read as much of the textbook and the class notes as you can, watch videos from the previous class offerings, and there's a homework due in 1 week, which is the second part of the exercise, the traveling salesman exercise that you did as homework for this time. It's going to be basically solving a traveling salesman problem using some kind of a rollout method and execute the rollout algorithm and do various things around it. So I think we should send an announcement out about the homework, but this is what's going to be. Okay, see you next time.